Hey everyone, how are we doing? It is time for some office hours. Make sure that audio might be in the background on that. You never know who is here. We can get some work done, do some work, looking over everything. So many emails. Oh, wait. Headshots. Yay. Just saw my emails. They look okay. Every time I get headshots, I'm like, how do they look? Look like my brother. as you get older, you look more like your family. That's the way it goes. Looking older. Well, let's see right here. If anyone jumps in with some questions, we're going to load up my Pearson. Sign into your course. Sign into your course. Sign it in. Oh, I think I know what it is. Okay, there we go. Signing in. Who is here with questions? Who is here? Let's see. Need to look at the grade book. Any questions in the chat? Instructor gradebook. Okay, manage incompletes. Gotta make sure these. Oh, pretty good. People are doing the work. Maybe they put down the work was due yesterday. So they already did it. But pretty good. When is chapter 13 due? That's due on the 27th or the 23rd. So there's 2 due tonight. No, tomorrow's another one due. We could do sampling proportion. We could do the homework. Not a lot of people have done that yet, so I can mention it tomorrow. Hey, Peyton, you want to chapter? What do you want to do? Give the questions. You got it. It's for you. Thank you, Peyton, on the Discord too. Throw you some points here. I think Mewbot's awake. Yeah, Mewbot's awake. Which one do you want to do, Peyton? You name it. You're here. Whatever questions you have. Chapter 12 quiz. Chapter 12 quiz. You purchased a 5-pack of light bulbs, and you want to see if at least one is broken. Here we go. Let's go do it. One of my favorite questions right here. Let me mark it in the notes, and then we'll do the next question. Get those hundreds. Get those hundreds. Okay, so you purchased a 5-pack of light bulbs. Okay. 343. Stat 201. Chapter 12 quiz. And it is... You purchased a 5-pack. Okay. So these are at least one questions. And whenever you do an at least one question, you have to have a strategy for solving them. So you have to write a sentence. And what do I mean by that? Well, you're going to write a sentence here that goes the following way. At least one is defective. Now, what else is the other possibility? Either at least one of these light bulbs is defective or what? Either at least one is defective or what? You have to think everything else that could occur. And what do I mean by that? Let's say you purchase 2 light bulbs. Well, if you purchase 2 light bulbs, it's either the case out of the 2 light bulbs that they could both be defective, that one could work and the other could not, that they could both work, or the other works, the other one's not. Well, either at least one is defective. Well, if they're all defective, then at least one is defective. So think about this scenario where they're all defective. So either they're all defective. Either at least one is defective, which would be these scenarios right here where there's at least one defective, or they all work. Does that make sense? We're just talking about 2 light bulbs because it works for 2 or 10 or how many light bulbs we're doing. So either at least one is defective or they all work. So now when we change this, we're going to turn they all work into the following. The probability that all 5 light bulbs work. So the probability of a light bulb being broken is equal to what? And defective, broken. We could say defective because they use that terminology, defective. What's the probability of a defective light bulb? Oh, yeah. All right, we'll do the late to class one. You got it, Maddie? Thank you, Maddie, for being here. You got it next. What's the probability of the light bulb's defective? It's in the question itself. The probability of light bulb's defective is what? Probably defective. You got it. So the probability it works is equal to 0.82 because it's either defective or it works. Defective means doesn't work, so they're complements of each other. What is the probability every light bulb works? Remember, we're purchasing 5 of them. So one of these things must occur. It's either the case that at least one is defective or they all work. What is the probability they all work? The probability they all work would be what? So the first works and the second works. So you buy 5 light bulbs and they all work. So you get a 5-pack, however a 5-pack looks. I guess there's this one empty slot. But the first works and the second works and the third works and the fourth works and the fifth works. All 5 light bulbs work. So what's the probability all 5 light bulbs work? So they all work means all 5 work. What's the probability of that? The first works and the second works and the third works and the fourth works and the fifth works. Because we're almost there. What's the probability they all work? You got it. That's the probability every light bulb works. And then algebraically, if that's a word, using algebra, we can just subtract this from both sides. I never do this. Like, people get mad. They're like, wait, what? Or at least back when I was in school. Because this keeps it equals. Like, doing this mathematically keeps the equation equals because you're subtracting both from the same side. So these are going to cancel out right here mathematically. And now you get 1 minus 0.82 to the 5th power is equal to at least 1 defective light bulb. So that has it. I thought it was going to make the dash look nicer, but I lie. Didn't do it. Sure. Okay. So that's the answer is 0.82 to the 5th power. 2. What? 0.82, 2, 3, 4, 5, and then 1 minus. That was not 1 minus. 1 minus, that is the answer. And there we go. That's done it. So what is, we have the next question about the student being late to class. That should do it. See if we can find it. I think that question's about here. No, it's not. Drop another question in the chat. The student late to class one is not too big. It's a little tricky, but we got tons of time here. So drop more questions. If you're working on a question, you just put it in the chat and I'll explain how to do it and I'll show the math and I'll draw it out. So you can get a video on how to solve your problem, but just drop your problems in the chat. And then notice how to solve them. What's the probability the person watch a football game also watch a basketball game? Yeah, those are good, but they're not on the test kind of. But let's do them. We got that question coming up here next. So a student figures. We need to teach you more things than just what's on the test. But I love every question where I'm like, ooh, this one's kind of like a test one. The wording confuses me. Let's do it. Thank you, Peyton, so much. Let's do that one next. A student figures they have an 84% probability of being late to class. If they are late to class, then there's a 25% probability they miss the train. So this is kind of compounding it. What is the probability he gets out of class late and then misses the train? So you need to get out of class and then miss the train. Do you hear the word in between this? Get out of class, something, miss the train. Because, and it's saying, if you are out of class late, you have a 25% probability of missing the train. What word did I say? Like, he gets out of class late, misses the train. So gets out of class late, and then I used a word. So what was the word I said? Gets out of class late. I said something between it, misses the train. Do you remember the word I said? I'll tell you in a moment. I'm getting some notes up here to help you see what we're going to do. And here's the hints. What word did I say? Did anyone hear it? 5,000 points if you heard it. The word was and. He gets out of class late and then he misses the train. Using and means we're doing multiplication. Now, the multiplication rule requires things are independent, but it's telling you the new probability because the probability of missing the train is dependent on if he gets out of class late. So it's updating that probability. Like, let's say he gets out of class on time. What do you think is the probability he misses the train? The probability of missing the train would be what if he gets out of class on time? And we can actually map this out. What's the probability? So it says class late, I think was probability of class late, probability, probability of class on time. Okay, so you're either out of class late or you're out of class, looks like his professor gets out of class late all the time. And then afterwards, if he's out of class late, the probability of missing the train, I think, well, they said it, is equal to 0.14. And then the probability of making the train is going to be the complement of that, which is going to be 0.86. Or no, it's 0.25. Using the numbers from the problem. I'm making this more complicated than it is by showing you every possibility. And then the probability he makes it that percent of the time. So now the probability of class on time, the probability of missing the train, I'm going to put to 0. And the probability of making the train is 100% because he makes it all the time if he's on time. So if you think about this, there's 4 worlds we live in. Who sees the 4 worlds? If we color coded here, you got class late, class on time. And you've got miss the train, which we'll do miss the train in red. So it could be the case that he gets out of class late and he misses the train. It could be the case that he gets out of class late and he makes the train. It could be the case that he gets out of class on time and he makes or misses the train. Who follows me on this? Just a yes or no in the chat. So this is class late, on time, and this is miss, and this is make, miss. And what we have right here, if you do the probabilities of these and just start multiplying through, is since he can never miss the train if he gets out of class on time, this is equal to 0. You just multiply these probabilities. You just literally multiply those numbers right there. And the probability over here is going to be equal to 16%. So 16% of days he gets out of class on time and makes the train. And then class late and miss, we just times this by 84 times 0.25, and it's 21% of the time. And here's the thing. If this is 21% of the time, then the remaining amount we can just subtract from 100 because this is a sample space. That's what I wanted to show in this problem, is that if you add up these two numbers right here, you see that 63 is the remaining, and you can also solve the math of 75 times 84. So you could do 0.75 times 0.84, and you can get that number right there. But this is the sample space of everything that can occur. So this is the sample space. Sample space of everything that can occur when he gets out of class. Sample space is every possible thing that could occur, because once you know the trick for this problem, it's too easy, as in someone might only watch this problem and be like, oh, so all we need to do is multiply 0.84 times 0.25, and there's the answer, and you're done. I wanted to go into more detail. So that's the quick solve. Once you know how to solve that one, you get that one on, you're like, oh, you just multiply the numbers. But you got to know what you're doing and why. It's the probabilities that you're associating with it, the probability of class late with the probability of class on time. And so this maps out everything that could occur with associated probabilities. These are dependent probabilities. We are able to multiply them because we have the new probabilities. Because the probability depends, it doesn't stay the same. It's a little nuance to everything right there. It's a little tougher because of that. Yeah. Okay. Then the next one is the football question, which I think is towards the end. It might be one of the last ones. This one's very similar. It's kind of the same twist on it. Drop another question because we're out of questions. Blood type one we haven't done yet. We did the Mars candies yesterday. We can still do it again we haven't done the car ones yet. Someone's stuck on the car questions. But drop another one. The probability of Deltman. Oh, well, there's the blood pressure one. We know where that one's at. We'll do it next. That's the last question. Here is the basketball one, right? 2015 study about the cell phones, right? What is the probability? Oh, wait, this isn't what is the probability? It's very similar. All right, here it is. Here we go. Thank you both for being here. Hopefully, I want you to get some hundreds. And so let's do this one. We'll talk over it and talk about what you learned and how it relates. It's kind of the point of the office hours, too, is to say, like, what have you learned and how does it relate to doing this? Okay? I think we're good to go. What's the probability that a person likes to watch football, given that she also likes to watch basketball? So the given part of this, when it says given they also like to watch basketball, you have to go within here and do given somebody likes basketball. How many people like basketball? Just answer questions. Boom, quick questions. How many people like to watch basketball? How many people like to watch basketball? I got Top Chat on, so it takes a moment. How many people like to watch basketball? 38. So with 38 people liking to watch basketball, what would be the probability of somebody liking to watch football given that they like to watch Rotowave bomb, all those points. Rotowave bomb in the chat. Still practicing those stats. What is the probability that they like to watch basketball? Oh, football. What's the probability they like to watch football? Thank you, Rotowave, for swinging by. You can't sneak in, Rotowave. I see you in the classroom. I see you over there. You sat on the left. I know where you sat. Right there. Shouts, Rotowave. 201, 320. Maybe other classes too. No, I'm so happy. Every year I teach over 1,000 students. And I probably remember 50 of them. You're in the 5%. The outlier. It's tough. It's tough to remember students after years. But if I saw you around town, I'd know you right away. You know that. I saw you down there for the events and stuff. No, I like that. I want to remember as many as I can, but it's tough. One year I taught 2,000 students. But what is it? The probability of liking basketball, given that they like football, is what? You're an outlier. Being an outlier can be a good thing. And the probability of liking football, given they like to watch basketball, is 24 divided by 38. And there we go. There's the answer. 24 divided by... You got it, Peyton. You got it. Yeah. I'll take 5,000 points for that. Let's do the next one. We're going to do the blood pressure one next. Sometimes it's like, wait, is that it? It's like, yeah, that's it. Okay, let's do it. Here we go with the blood pressure one next. This is a very similar problem to the last one. So the probability is an adult male. And if I pick a wrong one, because there's sometimes similar wording ones, but I think this is the one Maddie wants right here. So yeah, just practice. Don't worry about getting things wrong. I throw points. Just keeps you active in the chat. Okie dokie. Fallout Season 2 coming out eventually. Amazing. Okay. So this adds up to 100% right here because it's a valid probability distribution. And here we're going to do this real quick. We're going to put it on the side of the screen. A valid sample space, once again, adds up to 100%. So if you have a valid sample space, nice. You know it's a valid sample space when you look at it and it adds up to 100%. So valid sample space, add up the probabilities. They should sum up to 100% or 1.0 as a decimal. Valid sample space, we could check the math, but it does work out unless they've tricked us, but I don't think they have. So yeah, 3, 6, that's 6. Yeah, it all works out. What is the probability someone has both conditions? So what's the answer? What is the probability? We're looking at the first question over there on the left. What is the probability someone has both conditions? There you go. What's the probability someone has both conditions? Well, so this is a grid of like, do they have okay cholesterol, okay blood pressure? So what's the probability of both? Yep, 0.19. Great job. Why did it change my aspect ratio? What is the and so the next one says, the probability that a man has high blood pressure is what? So you have to think which of these individuals have high blood pressure. This actually uses the addition rule. If I show you, I think you'll know it. What is the probability someone has high blood pressure? Now this uses the addition rule because you can't have high blood pressure with high cholesterol, and you can't have high blood pressure with okay cholesterol. Those are disjoint, as in you're either high blood pressure, high cholesterol, or you're high blood pressure, okay cholesterol. So what's the answer here for the probability someone has high blood pressure? Exactly. We just add together those probabilities. And what's it changed? Oh, it didn't change. There we go. If I get a math wrong, just tell me. Brian, you did a math error. So the next one says, what is the probability that a man with high blood pressure has high cholesterol? So it's like given he has high blood pressure, so you only focus in on this part of the table. Do not look at anything else because now this is the only part of the table that matters. This is the new 100%. So someone with high blood pressure, what's the probability they have high cholesterol? Go ahead and see if you can figure it out. Drop the answer in the chat. But the probability of them having high blood pressure, high cholesterol, the probability of having high cholesterol given they have high blood pressure. It's pretty good to add this up right here to get the total percentage. 32% of people have high blood pressure, which we did find earlier. And what do we do now? Kind of drawing it out for you as you. That's it. Yeah. So what's that gonna be? That's gonna be like 63.333333333. No, it's gonna be close to that. It's very 63.5. That's what I say. Let's find out. 63.5. That's my guess. Oh, it was close-ish, but not close enough. That's a horrible guess. What am I doing? I wouldn't have gotten it. Okay. The probability that a man has high blood pressure if it's known he has high cholesterol. They're mixing up the wording, saying it is known he has high cholesterol. So it's known he has high cholesterol, which equates to 42%. Yeah, 42%. So it's known he has high cholesterol. What's the probability he has high blood pressure? And once again, you ignore the rest of the table because we're only talking about we know they have high cholesterol. It says if it's known he has high cholesterol. So that would be the known fact. You would know they have high cholesterol. Yep. Nice job. Are these a lot easier now? Like once you see like, okay, you just narrow in on that. I think once you see the way of doing it. So that one should be less than, that should be like 45.4. That's what I say. 40. Oh, it was so close. Would I have guessed it? Here's my guess. Oops, that's not right. 45.4. Would I have guessed it? Nope. Unless I've done another math error on here. Yeah. Very close. It looks like you have to be very exact. Can you even be 1 decimal off? Nope. You have to be very exact. Careful on your rounding. If you do get something wrong via rounding, let me know. I'll probably give you the points back, especially if it's just like that. But those would be very hard to guess since there's no margin of error. Really, there should be like a thousandth margin of error. Okay, the next one is a 2015 study. There's a few of these. These are the cell phone landline ones, right? Let's go find them. They're around question 13 or so. Boop. Drop more questions because that's our last question right there. We might try to do the car questions too because we haven't done those. New. In a dresser. Let's see how next. Oh, they're further back. Oh, no. Here we go. Okay. A lot of different ones in a dresser. I already said that. And if I miss a question, please let me know. I forget things. Okay, the time is 23:13. Let's do this. So this one right here is talking about people who have no landline. Now, what you want to do when you work these questions is write down the probabilities. And the best thing to do is to go right here. Nice. Oh, that's a good one, Peyton. I like that one. Not that I don't like any of these. The probability of no landline is equal to 0.51. So what's the probability of landline? If the probability of no landline is 0.51, we have what is called the complement. The complement is 1 minus. So either you don't have a landline or you do. So the probability of landline is this. Now, we are going to 10 houses here. So there's different versions of this. Yours might look like this or might not. A few of them start out with this whole 2015 thing. With 10 houses, we want to see the probability that all of them have a landline. So the first house has a landline and the second house has a landline, and technically they need to be random houses. But what word do you hear? Peyton's already done it. The first has a landline and the second has a landline. And when I say and, that's multiplication. And you have to assume the houses are independent. Once again, check out the rules. The rule of multiplication requires independence. And there's questions on the test that literally are that simple, meaning the first house having a landline would not influence the second house, which is not truly real, because if you live in an area without landlines, then you're probably more or less likely to have landlines, less likely in that instance. And so Peyton's right. This is the probability of a house having a landline occurring 10 times in a row. What is the probability that at least one of them does not have a landline? So either at least one does not, or what, Peyton? Either at least one does not have a landline or what? Either at least one house, or they all do, or all do. You know what we just figured out? We just figured out all do, which the probability of all them having landlines is this. So we're just going to do 1 minus that. So this is, we're answering number 2 right here. We're currently answering everything in here is this answer. It's a lot of work. So the probability of this, so this is, we'll abbreviate at least one does not. And so 1 minus everyone having a landline is the probability of at least one does not. What is the probability that at least one of them does have a landline? So either it is the case, we're almost there. And so then we'll put this inside of this box. It is either the case that at least one does, or what? It's either the case that at least one has a landline or what? either at least one has a landline, like maybe 5 houses have landlines, or all of them have landlines. Either at least one house has a landline, or what? What is the other thing that could occur? You go to the houses, either at least one or all do not. Yeah, no landlines. So no landlines. And this is going to be 1 minus no landlines. And that is equal to at least one does. And so that's 1 minus 0.51 to the 10th power. Does Peyton, do you follow all this? It's the writing the sentences that you have to practice to be like either at least one does not have a landline or they all do. Either at least one does have a landline or none of the houses have landlines. So 1 minus no houses having landlines. So yeah. And so let's make sure we do this right here. So the probability that they all have landlines. So having a landline is this. 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's 3 zeros. So I know it's 4, but just wait. I think it's that rounded. And we can see if we do 1 minus. That's the next one. Yeah, there it is right there. So you can see this right there. And then the other one is the probability that at least one of them does not have a landline. Wait, at least one of them does have a landline is everything but no houses with landlines. And so house with not a landline, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1 minus. Okay, we broke it. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 minus that. There we go. That should be right. Oh, you got to round it. Woo! Woo! Yeah, technically A and B are just complements. It's important to know why, but A and B are just complements. Yeah, because if you notice here, the answer to the first one is they all have landlines, which is every house has a landline. So in the second one, we say at least one does not have a landline, or they all have landlines. So 1 minus all having landlines is at least one does not have a landline. And then for part C, it's either the case that at least one does have a landline or none have landlines. So 1 minus none have landlines is equal to that. So this is 1 minus none having landlines, because none having a landline, not having a landline is 0.51. Peyton, how do you feel 1 through 10? Like 10 is like, I get what you were doing, or 1 is like, I have no idea. Anywhere in between. And then we'll do the next one right here. I think we're doing the dresser one. 8, good. Yeah, I've done a lot of those, and I think it really boils down to writing the sentences. When you can start to write the sentences more, it starts to make more sense. And then you're like, okay, you just have to, it's big practice. There's like a problem or two on the test that do it. It's not like it's not the whole test, obviously. But you should be able to solve one of those problems. It's a good theory problem. Like, it's just understanding, like, what is the complement and all that. I already marked, I think it's back here. Rolling a double. Here we are. In a dresser, there are 10 blue t-shirts, 8 red t-shirts, and 7 black t-shirts. Give me back my black t-shirt. No one knows that song anymore. It's this shirt. How many t-shirts are in this drawer? How many t-shirts are in this drawer? How many t-shirts? So we got 10, 8, and 7. Start drawing it out. 10, 8, 7. 25 t-shirts. That means a red t-shirt is going to have 8 out of 25, and a not black t-shirt is going to be 18 out of 25, because we would do 25 minus 7 to get 18. So because the black t-shirts are 7 t-shirts, as you can see right here. And there we go, 8 and 18 out of 25 times by 4. So you can times by 4 to get the answer, because 25 times 4 is 100. And then 18 times by 4 is 72. So if I'm doing the math correctly, we got it. Once again, just if you want, just do 8 divided by 25 and 18 divided by 25. There you go. And there's the answers. I just like math. Lola, good to see you there. And Bubot throwing you some points. We got only one more question right now. So drop some questions. We only got supposed 65. I'll probably do the car questions after this. No one's asked them. Everyone like, are those car questions easy? There's 2 versions of it. One does the multiplication, one does the addition roll. But everyone's probably like, those are easy questions, Brian. Psh, psh. Easy questions. 31, 13. Traffic checks. Ooh, Maddie's got some good. I hope people are getting hundreds. I want to hear that. If you get 100, let me know. That always makes me happy to hear. Suppose. Here it is. Suppose 46% of families in the country own a tablet and 25% own a computer. You would think that, and this is a good like test-ish question. Could you just add it up and say the percent of people who own a tablet or own a computer is 71%? Don't look at their answers. What's wrong with using the addition rule here? What does the addition rule require? And what does it mean? Really good review question. What does the addition rule require and what does that mean? There's the answers on the screen. What does the addition rule require and what does that mean? So the answer is in here. What does the addition rule require and what does that mean? The addition rule requires what? Mutually exclusive. So to add these together, it would have to be the case that if you, and great job Lola and Peyton, it would have to be the case that if you own a TV, you can't also own a tablet. Is that the case? No. People can own both, which means they're not mutually exclusive. The test for mutually exclusive is if one occurs, the other cannot occur. Like, could it be snowing and 90 degrees out today? Like you say, man, it's 90 degrees. It's also snowing, yes or no? Could that be the case? Could it be 90 degrees and snowing? No. That means it's mutually exclusive, as in snowing mutually, like the mutual means together. The two things do not occur at the same time. Like if they were to overlap, that would be mutually inclusive. Like it could be below 32 and snowing. Those are mutually inclusive ideas, not disjoint. So these are literally things that occur at the same time. So you can't add them together simply. There are techniques and ways for it. But you can just see where it says not disjoint. I literally clicked that because I saw that they're not disjoint. So the addition rule does not apply. Once again, the rule for addition is disjoint. The rule for multiplication is independent. Make sure to know those rules and know what independent means. Funding for schools. Yeah, we got one more before that. We got the traffic checks. But Lola, thank you for being here. And Isabella, it's good to see you here. Oh, man, we're getting so many people. And thank you so much, everybody. I've been making it, I want to say this. Mental health is so very, very important. I have found that every day I need to go on a walk. I need to talk to people. I need to be outside for moments. You have to do that. And thank you. No one's ever gotten mad at me for being a little late to office hours. I do need to do office hours. I want you to say, hey, we're doing. I want that. But no one's ever been mean to me about it. And I really appreciate that because you got to go out. You have to go outside. You got to get some vitamin D. You gotta enjoy the world. It's like you have to. That is what matters in life, is like being there for each other, seeing each other, being in the world. School matters too, but school matters less. Your teacher didn't say that, but I did. So number one thing is, are you happy? Are you well? That's what we do. We did the bowler one yesterday. I haven't done the Red Cross one. Traffic checks. But everyone here is awesome. Traffic checks. We're going to have big office hours tomorrow, too, because we need to do the Chapter 13. Isabel, we could do that towards the end. We might do that, Isabel, because that's due coming up here soon, too, right? So we need to get that done. Traffic checks on a certain section of a highway suggest that 90% of drivers are speeding there. Since 9 times 9 is 81, move the decimals around, the multiplication rule might suggest that there's an 81% probability that two vehicles are speeding in a row. Does anyone here drive a lot? Just type yes in the chat if you drive a lot. Who in here drives a lot? Like I drove to work today. I got on Alcoa. Yep, Lola. So you ever get on the highway and you're like, I want to go fast. Don't go too fast. But when you're driving, the speed of your car is really what's on other cars. The speed of your car, what's on other cars. This is you. This is your car. You got some cool tires. The speed of your car depends on other cars. So it's not independent. So you can't just multiply the probability of two cars being in a row because how fast you are able to drive. Like you can't speed if traffic's all jammed up. So you can't really do this. The reasoning is wrong. There are cases where the speed of one car is not independent of the speed of another car, so the multiplication rule does not apply. because to use the multiplication rule, you have to have the two things are independent of each other, and you can't reasonably assume that each car is independent of another car. No, Peyton, no. Oh, yeah, I'll tell you a quick story here. I was driving to work this morning, and I was only going like 5 over. And I wasn't in the passing lane. It's 4 lanes. And I'm over here to you, on the second most lane on the outside. And I'm going like 5 over. And I'm about to go over to the right lane because I got to turn off. I got to get on to Kingston Pike, all that good jazz. And somebody comes by me on the right going like 15 over, and they don't even take the exit. They're just on the farmost of 4 lanes going 15 over, passing me. And I looked over before I went into the right lane. I'm like, this person's speeding up, going right down 15 over in the farmost right lane. So I didn't get over because I was like, if I get over, they're going to hit me. No, I got over. But I was like, why are you going 15 over? And they just flew by me. Don't hit people on the highway. Don't do that. Favorite songs. Do I miss one? Funding for schools. Okay, let's do funding for schools. Story time with Brian. Brian almost... You got to be careful. You have to really... You don't want to be too, afraid while driving. You have to be aware. Don't be afraid. Be aware. Fear will tense you up. Awareness will keep you from turning into the exit lane when you're trying to exit and someone speeding by. Okay, funding for school. Oh, no, tell your roommate to chill. I mean that. Tell your roommate to, if you're going to go fast in the fast lane. People expect that. Driving is it's sadly, sometimes people, you look down at your phone too much or something. I'm not saying you, but you get what I'm saying. Like, people learn because they have an accident, and that's not how you want to learn. It's not, So Peyton, tell your roommate, be like, no. Yeah. Okay, let's do this. Funding for many schools comes from taxes based on assessed values of local properties. People's homes are assessed higher if they have extra features, such as garages or fire. I guess a garage is an extra feature, right? Guess I'm lucky. I grew up with a garage growing up. My parents had fireplaces too. Nice. Middle-class family. Assessment records in a certain school district indicate 20% of the homes have garages and 9% have fire. Really? Oh, interesting. The addition rule might suggest that 37% of residences have garages or a fireplace. Okay, what's wrong about doing this? What's wrong? Don't read their answers. What is wrong with this? Don't read their answers. To add up the probability of garage or fireplace. Running over a wire. Garage or fireplace. What's wrong with this? Because they just added it. Garage or fireplace. What's wrong with adding it? They can occur at the same time. You can have a garage, also a fireplace. So they're not mutually exclusive. They're not mutually... Well, but also probably having a garage would make it more likely to have a fireplace because they're like a wealth thing. Like people with garages, like if you only have a carport or just a driveway and you don't have a garage, you'd be less likely to have a fire. I'm not saying you won't, but you think about like, oh, we have a 5-car garage. I don't know, like billionaires talk. Oh, we have a 5-car garage. They probably have a fireplace too. They might not. They would just be more likely. And that would be the multiplication rule, which we can't also do because that would be having a garage and a fireplace. Sounds right. Yeah. That'd be having a garage and a fireplace. But you can't do that because they're not independent. But the addition that they're doing, because they're adding them together, can't be done because they're not mutually exclusive. And the way to check mutually exclusive is to say you can have a garage and you can also have a fireplace so they can occur at the same time. If they were mutually exclusive, it would be like snowing and 90 degrees out. Because if it's snowing, it can't be 90 degrees. Does that make sense? Like you could say, well, what if like the snow's like sub-zero, like absolute zero? No, don't come up with some crazy thing. If it's 90 degrees, it's not snowing. It could be the case that someone has a garage and a fireplace. So that would be it. We had to close our fireplace because of the family of possums. Oh man. We got our house and our fireplace had issues, and that's a long story. So we don't have a fireplace. My wife loves fire. Some of the probabilities to events? No. It's no. Disjoint. We can't do it because they're not disjoint. The addition rule requires things are disjoint, and we can't do it. I don't have a working fireplace. Need fire. Favorite list of songs I think we're doing next. We'll try to get to some sampling distributions. Have we missed any? We haven't done the car question, but no one said it. So you know what? If we've done a lot of questions. We might do sampling. Do you want to do sampling distribution homework? Who wants to knock out sampling distribution homework? We could do the full sampling distribution homework in this video. Because if no one came in here with the car questions, I guess we're not doing them. I got videos on them. But we've done a lot of these. I think we haven't done the car ones or the Red Cross one. But they're all very similar. They're all, like, we've done versions of things. Like, you could figure it out. Okay. Do we want to do the sampling distribution next? We have time. We can do the full homework. So I think it was Lola. Full sampling distribution homework. Here we go. You have these many songs on your playlist. Nervous Kicker? Yeah, let's do Nervous Kicker next. You got it. So there's 6 here, there's 8 here, there's 2 here. You have a total of 16 songs. What's the probability a rap song is played? 8 out of 16, so 1/2. What's the probability it's not country? That's going to be everything but country. If you add up this, you get 14. And so that's 7/8. And an 1/8 is 12.5, so it's 87.5. So 50 and 87.5. Divide the numbers, you will get 50 and 87.5. There we go. Nervous Kicker. What are we doing next after Nervous Kicker? If people tell me to do... This is where I love. We get to the math stuff. Math is so fun. We did bowling yesterday, I think. We did bowling. And the Mars, for anyone watching this, probably people don't watch the in-between sections. The Mars candy one and the blood type one are virtually identical. The blood type just has harder numbers. Just worse numbers. Nervous Kicker. Here we go with nervous. Oh, I didn't put the timestamp. That question only took a minute and a half. 41:23. Nervous Kicker. Okay, what are we doing after Nervous Kicker? What, Lola, was it you or Isabella who wanted to do sampling distributions? I'm deciding right now if I'm going to do sampling distributions or do the car ones, and it's your calls. I don't think I don't think it was me. What do you guys, gals and pals here vote? Should we do sampling distribution homework next, which is due tomorrow, or should we do the car questions and the Red Cross? We have time to do like cars and Red Cross, or we have time for sampling distributions. Okay, let's see right here. This is the Nervous Kicker one. A Nervous Kicker makes about 63% of their field goals attempts. If they make the first one, sampling, let's do it. If they make the first one, their success rate increases to 93%. So what is the probability they make the first one, and then with a 93% probability they make the next one? So they make the first one, and then, do you hear the keyword? And then they have a 93% probability of the next one. It's not the first one's 63, and then the next one's 63. The probability changes. So the first one is 63, and then the next one is 93. So what is it? The answer is going to be about 58 or something. I think Lola figured it out. When I say that word, when I say what's the probability they make the first, and then with the new probability they make the second, I'm saying multiply. I know you're saying, but wouldn't it depend? Yeah, but we have the dependent probability. So that's where they're giving you the new probability that depends on them making the first. And there it is right there. So there's the answer. Just multiply the two numbers. If you know the trick, yeah. Once you know the tricks to them, or like what exactly they're asking, way easier. Well, we're going to do some sampling distribution. So 2 seconds right here. 2 seconds sampling. I think we can do the full homework. That's my goal, is to do the full sampling distribution homework and then tell people tomorrow, be like, it's in the video. Because I understand these can be tough. And yeah, it's like, how in the world do I do this? What is it asking? 8 questions. Here we go. Full sampling distribution homework. Okie dokie. 45, 33. And let me type it out. Stat Tool 1, Chapter 13, Homework, Question 1. And everyone gets these. Okay. So when we are doing sampling distributions, the sampling distribution is said to be normally distributed if it meets certain conditions. So I'm not even going to read this question basically. I should. But I know if I'm doing a sampling distribution, it meets the conditions of random, 10%, and for this one, success failure, it'll follow a normal, which is unimodal symmetric. Now it asks what the mean of the distribution is. For the mean of the distribution, you do get a formula sheet on the test, and the formula sheet shows you right here that the mean for the sampling distribution of the sample proportion is mu p hat equals p. We went over this last class. So we need to find where p is. Remember, the equation for this is going to be mu p hat, which is the quantity being asked for right here, the mean of the sampling distribution. That is the mean of the sampling distribution of p hat. And the answer is, it is p, and it says suppose the true proportion is this. So the answer is 0.43. It's because mu p hat equals p, and it just told us what p is. So that's the answer. It's right there. So the mean is 0.43, mathematically. Next, we get the standard deviation of the distribution. So the standard deviation is p times q over n square root, and that is on the formula sheet. So the standard deviation of p hat is equal to p times q over n square root, and this gives you variation. So we know p is equal to 0.43. Its complement is q, which is equal to 0.57. So we simply plug in 0.43 times 0.57, which are p and q. We divide by n, which is 241, and we square root it to get the standard deviation. It's going to be about 2 or 3%. So p times q over n square root. Don't forget to square root it. Most common error people do. P times q over n and square root. 2 or 3%? 3%. And we drop it in, we move the decimals, and we make sure it's right, and we check our answer. That was that. That's how to find the mean and the standard deviation. Once again, you know it's normally distributed if you meet the conditions. I also want to say a lot of people make a mistake thinking meeting the conditions means it's normally distributed. You don't have to meet conditions to calculate p hat. That's on your campus content. Also, it says meet conditions to calculate the mean. You don't have to meet conditions to calculate the mean. You meet conditions to state it's normally distributed. If you meet the conditions, it's normally distributed. If you don't, can't say it's normally distributed. Okay, so the first one right here, this is actually covering, question number 2 is covering the success failure condition. And this original distribution right here, I think it says is, does it say it's skewed? Doesn't say it's skewed, does it? Oh, we can view it. That's how you can view it. It's skewed to the left. Now, with this question, I was like, I swear it asked about skewness, but there's another way to tell, which I'm not going to get into. With this question right here, you can see that it starts to normalize as n gets bigger. And this is the central limit theorem, which we're going to cover more next class. They don't really talk about it in this part of the chapter. I wish they did. But as n gets larger, and this is the meeting the condition for normality I was talking about, that if we meet the conditions of a success failure, we'll talk about what that means here in a second. If we have a random data set, we sample less than 10%, we have at least 10 successes and at least 10 failures, the 3 conditions for the distribution of the sample proportion to be normally distributed. You're welcome, Isabella. You can check it out later. And thank you, Isabella. 5,000 points for texting that right there. Anytime. Just you jumping in here asking this, it's in the video for you to see later. And you can see it eventually gets normally distributed. Now, the proportion of this is 0.85, which means the problem is going to be the failures. If P is 0.85, Q is 0.15. They're complements. They add up to 1. If P is 0.7, Q is 0.3. If P is 0.6, Q is 0.4. They add up to 1. It's the true proportion of whatever you're viewing. Like the true proportion of in-state students here at UT is 0.6. 60% of students are in-state. This question says the true proportion of whatever we're doing is 85%. So what we're not looking at, the things that can't be read apparently by this reader, is 15% is not read. That's where we're going to have not enough successes. So if you look at this right here, with 20 observations, you would only expect 3 successes. You have to have at least 10 successes for it to pass. With 50 observations, you would only have at least 7.5 failures. And I said failures, but successes would be the other side of it, the 0.85 times it. Now, with 75 observations, you would have 11.25 failures, and we can check the successes, but it's the bigger number. You'd have 63.75 successes. And to make it very clear, We are mathematically solving for each one of these. Each one of these is an n. So each one of these is an n. And we're timesing it by P and Q. P is 0.85, the probability of success. Q is 0.15, the probability of failure. And we're seeing if NP is greater than or equal to 10 and NQ is greater than or equal to 10. This is the success failure condition. And if you don't meet it, the data is not normal. This did not meet it. This did not meet it. And since this one met it here, then this will be normally, or like it's normal enough. And this one also meets it. There'd be 15, because you can times this by 0.15. So there'd be 15 failures and 85 successes, which is at least 10 successes, at least 10 failures. And that answers the whole question because now, oh, it asks where the center is at, right? Doesn't it? So to view the center, it's not that hard to do. So the distribution is skewed to the left. Monster Man. Monster Man's gonna be mad if I don't draw him. Monster Man right here. You got that Monster Man right there. Left, right to the high, left to low, whatever way the Monster Man's tail goes. And so it is left skew. And then the center is the peak, and that is between 8 and 9. Because, and you can zoom in on it. You see this is 0.9, 0.8, so it's between 8 and 9, where the peak is at. So it's between 8 and 9, and then it has a large spread from 0.5 to 1, which is, you'll see right here, greater than 0.4. So that should be around that one. The next one's also skewed left because it didn't reach the success failure condition being met. The center of it is wherever the peak is at. The peak is right there. So that's 0.7, 0.75, 0.8 to 0.85, 0.8 to 0.85. And usually, I can't promise, usually this is contained, but it might overlap. You have to see where the highest peak is at. That's the answer. And it has a spread that is 0.35. You're just subtracting these numbers right here. So you notice those are 0.35 apart. So the spread right here is there. That's the spread. And the next one has a spread of 0.35. Also, the peak is in here. That's going to be a harder peak to find. This is in units. Each one of these is a unit of 5. So that's 70, 75, 80, 85, 85 to 87.5. So it is now normal because it met the conditions, and 85 to 87.5. And then the spread was the same as last time because this is 0.35. This one has a smaller spread of 0.2. No worries. We're doing a hard question right here. A lot of parts. And this one is normal also because it meets the success failure condition. It's likely that the answer is this because 0.85 is contained. I've rarely to never seen 0.85 not, or whatever this is, the truth not in there. It should be, and we should see a peak right there. My guess, you can count it out, but that is probably right where it's at. Rolling a fair dice. Yeah, we can try to. We have enough time. Let me see. Let me see if I can do a bunch of these, Maddie. Let me try. And then the range is smaller on this one. What does it say? Explain what random means. And tell me if Maddie, if something says this. Random would mean that you would expect, not that it will roll at 1/6 of the time, but in the long run it'll roll at about 1/6 of the time, but you don't know what each individual dice roll will be. Does that look like an answer, Maddie? That you would expect it to roll 6 about 1/6 of the time, or all numbers would be equal about the same amount of time, and then you don't know what will occur next. Like the previous trials do not indicate. Tell me if that looks right, and if you get it wrong, let me know. 0.2 is the range on this bottom one. 0.2 is the range. 0.2. 0.2. So this one. Awesome. Okay, let's see if we can do it. We get the fall and draw more questions, Maddie. I'll have my dual core brain going, trying to. Thank you, Maddie. 5,000 points for being here. Pew Research says that 45.1% of people, teens or whatever, report being online almost constantly. That's not good. And explain what p hat of 0.451 means. P hat is the sample proportion. You have to know notation right here that p hat means they took a sample. So make sure you know that the formula for p hat is x over n. Like theoretically, they could have talked to 1,000 people, and x could be 451, and then 451 divided by 1,000, which is x over n equals p hat. So the p hat right here means in a sample of whatever, there it is, their sample, 51% of the sample reported this. So 51% of the teens in the sample reported. That looks about right. What does the other one say about this? That looks close. This is the researchers. It's the researcher's best estimate of the truth. So it's not an p hat is not an estimate of p because p hat is an estimate of the truth. P is the true proportion, which is the percent of all people who think they're online constantly. Now it says to calculate the standard error. The standard error uses p hat instead of p. So pretty easy to calculate this. It's going to be a little math. So the small difference in this formula is the standard error. I did standard deviation. Standard error p hat is p hat times q hat over n square root. And so you just do q hat is equal to 1 minus p hat. And so q hat is equal to 0.549. And because p hat is equal to 0.451. And so now we do 0.451 times 0.549 over 1058 square root. There it is, p hat times q hat over n square root. And square root. There it is. There's the standard error. 5 decimals. It's so crazy. 30. That's right? There we go. And then what does the standard error mean? The standard error is an estimate of the standard deviation. It's variation within what we might expect from different samples. Nice job, Maddie. Got them all done. The standard error is the best estimate of the standard deviation. So it's either this one or the lower one, which measures the amount of variation in sample and population. Which measures the amount of variation in sample. Yes, it's relative to a sample size. So if you notice the math right here, the math included the sample size. So it's relative to the variation you would expect to see within samples of this. So it's an estimate of the standard deviation. So it uses p hat instead to estimate what you might see in samples of that size. There you go. As the sample size. Oh, that's this question too. Oh, I think we might have easy questions from here out. As the sample size increases, the mean of the distribution will do what? It'll stay the same. Because when you look at the equations right here, this does not include any sample size. There's sample size for standard deviation. Standard deviation gets smaller. But the mean, which is mu y bar or mu p hat, it'll stay the exact same. It will not change. So 5813, it will not change. It'll stay the exact same. It stays the same. Standard deviation gets smaller. Might say. Another easy one. Well, I think we're going to have this done. Okay. Suppose, I need to mark this though. Suppose. Oh, timestamp. I've one time tried to make it so I could timestamp stuff without typing them in. Didn't work. Suppose 30% of people in a town walk and talk on their cell phone at the same time. If you were on a busy road and you watch 50 people drive by, what is the proportion you would expect to see walking and talking on their cell phone? So this says expected proportion. So when it says what proportion would you expect to see, expected proportion to see, expected proportion is mu p hat in a sample of 50. So in a sample of 50, if this is the truth, then you'd have mu p hat. And this is not multiplied. That's saying the expected sample proportions. This is read expected sample proportion is equal to the truth. You'd expect to see the truth. So the answer is P. If 30% of people talk on their cell phone, you watch 50 people, you expect 30% to walk and talk on their cell phone. Yeah. Oh, this might be a longer one. No, this is success failure condition stuff. I don't think it's longer. So once again, the 3 conditions are random, 10%, and success failure. Success failure means you need at least 10 successes, at least 10 failures. And so they're asking if the conditions are met. So Pew, which is a reputable group that does random surveys, so they met random, samples 1,600 people in the U.S., and that's less than 10%. And a lot of people get confused on the 10% condition. There's like, what is there, 350 million people in the U.S.? And so less than 10% means you can't sample more than 35 million if there's 350 million. So this is definitely less than 10% of the US. That is the 10% condition, sample less than 10%. Now, the success failure condition says we need at least 10 successes, at least 10 failures. But here's the thing. With 1600, the success rate is this. It's the probability right there. We expect like 427 successes, and the failures, you can do 1 minus. So very clearly, we have at least 10 successes, at least 10 failures. An automatic character, I think we did that one. Was that question number 2 or 3, Lola? It's in the video. It might be like, we meet the conditions, I think. There's at least 10 successes, at least 10 failures. We have at least, that says less. Oh, no worries, no worries. Oh, I got 2 more. Yeah, different, you got it, you got it. That was like question 2 or 3. I might not have enough time. Ah! And if not, we can do it tomorrow, Lola, or I'll find you a video. Let me know. Okay. Philanthropic organization sends out mailers, and looking at the histograms, what is the smallest possible sample size where you feel comfortable using the nearly normal? We have to meet the normal curve. We have to meet the conditions to pass this. So it has a 6% success rate. So you need at least 10 successes, at least 10 failures. So with a 6% success rate, you don't even have to look at the data. Because if you have 20 trials and 6% success, you only have 1.2. That's not 10. If you have 100, you'll only have 6. That's not 10. If you have 200, you will have expected successes 12. So guess what? When you look at the histograms, they should look really normal at 200, maybe a little at 100, but 200 is where you have at least 10 successes, at least 10 failures, because both NP and Q need to be greater than or equal to 10. So the math for this is you need for the success failure condition to identify N, which is sample size, which there are different N's here. And then you need to identify P, which P is 0.06. And then Q, which is, you don't have to do because it's the bigger one, so you're not going to have problems with Q here. Whichever one's the smaller one is the one you really have to check to make sure there's at least 10 of. And then you do NP has to be greater than or equal to 10, and NQ has to be greater than or equal to 10. If they both pass that, you pass the success failure. So the answer is 200. And when we take a look, it'll start to look really, it looks a little normal around 100, but 200 is where it actually passes. So we got to be careful. And it literally states it right here that at 200, we have at least 10 successes, at least 10 failures. The value of NP is at least 10. No, it's both. Both of them are at least 10. Yeah, at least 10 successes, at least 10 failures. And I think we've done it. I think this is it. We will now have done the full homework, checking the conditions, knowing the success failure. Gosh, we did a lot in this office hours. Woo! Okay, last one. We've got a machine right here with cans. Will be some variation, and they're looking at this distribution. Would a normal model be useful to explain this sampling distribution? It doesn't look normal. It's skewed. It's very skewed to the left, so the answer is no. That's it. Oh, wait. So what does it mean if we can't use it? Can't use the empirical rule. Can't use the 68, 95, 99.7. So the mean of this is this, and the standard deviation is this. Would you expect 99.7 to fall within 3 standard deviations? No. It's because it's based on the normal model. That's the empirical rule. So the empirical rule is based on the normal model. So if the data is not normal, you can't use the empirical rule. And that has got it. Woo! I guess it took a little while. It took like almost 20 minutes to do the assignment. But 8 questions, 20 minutes. So Lola, I hope any last questions? I'm going to run. I have class in 13 minutes. But I hope this helps out a lot right here. Gonna eat a last little bit of lunch. Take my medicine. Me and my RC. With that, you're welcome, Lola, and thank you. 5,000 points. Bye for now, everyone. Bye.